Yeah, dear friends, this is Dr. Prasad KNN, Professor and Head Department of Physics, PNMIT. So I would like to talk on high pressure studies on electrical resistivity of GETETL chalcogenide glasses. So before I go to the glass preparation part, so I would like to give some information about chalcogenides. So the way how, in a periodic table, we have uh, halogens. So there are chalcogens. So here we have taken chalcogenide glasses. Basically, chalcogenide glasses are semiconducting glasses. And apart from the semiconductors, we are going to add some chalcogens like the materials like thallium, tin, etc. So in my present work, so I have taken germanium, tellurium as base glass, and thallium has been added as additive. So that makes a ternary glass as Ge, Te, and Tl. So now coming to the method which is employed for synthesizing this glass is nothing but it's none other than conventional melt quenching technique. So for this we used a rotatory furnace and using which you can rotate horizontally, and for the sake of uniformity we can distribute heat throughout the samples, and this rotating furnace is maintained at temperature of the melting points of the ingredients like the starting elements like germanium, tellurium, and thallium. So these are the corresponding temperatures: 938 degrees centigrade, 449.5 degrees centigrade, and 304 degrees centigrade. So this is we have set the temperature beyond 1000 degrees centigrade so that the maximum temperature of all the constituent elements can be covered within. And now the furnace temperature, as I said, it is at 1000 degrees centigrade. And this material is heated at a rate of 100 degrees centigrade per hour, and which is done for a duration of 48 hours. And the rotatory furnace is rotating at 10 RPM. And soon after we did for 48 hours, so we got a bulk material, and immediately this bulk material has been thrown into a mixture of ice water and NaOH mixture, which is nothing but a quenching medium. And as soon as we thrown that, and it become a solidified material, so which is nothing but a bulk glass material. So this is how glass is prepared using conventional melt quenching in our studies. And in order to ascertain whether the obtained bulk material is a glass or what, so for that we went for characterization, which is nothing but X-ray diffraction studies. So we took a few samples as representatives of the series, and could you notice that there are no sharp peaks could be observed in the XRD spectrum, so which is very clear that this material is amorphous. And the amorphous nature is nothing but the nature of glass. So it is very clear that the bulk that what we prepared is nothing but a glass. So this is how a bulk glass material of germanium, tellurium, and thallium is being prepared with the help of conventional melt quenching, and the characterization is done with the help of X-ray diffraction. So now moving on to the next part, where we wanted to know how this sample as an entire family, where you could see there are 13 samples just by varying the thallium content as a percentage. So if you look at A, B, C, D, E, F as per the graphs, that there is a variation in thallium content, thallium 1, TL2, TL3, TL4, and so on. It goes up to TL13. So there are about 13 samples in the entire series has been taken by varying the thallium content. And then we plotted a graph by taking variation of electrical resistivity with respect to pressure in the entire series. So we noticed the following results, and that let me tell you what are the points that we noticed here. So we plotted a graph by taking percentage content of thallium along x-axis and the transition pressure along y. And then we could notice the following points. Number one, so there is a decrease in transition pressure, which is due to the metallic nature of thallium as compared to tellurium that it replaces. Electrical switching, ADS studies, and other many studies have indicated that thallium is present with two valencies, either a trivalent or a monovalent. So usually there is a possibility that these two valencies are seen in many of the experimental observations, a trivalent thallium and a monovalent thallium. So as a third important point, as it says, as the thallium content increases, as the percentage of additive increases, so which increasing monovalent species tends to fragment the network, and this may lead to enhanced compression at lower pressures. Also, it could be noticed that the pressure dependence does not show any change due to valency of thallium present in it. So these are the important results that I think we can draw, or we can get as inference by studying percentage of content of thallium versus transition pressure. So as a next important step that we went for, so we applied a very high pressure using diamond anvil setup, where lots of gigapascals of pressure is applied to our sample, whose size is typically about zero point 0.4 to 0.5 nanometer in size, or micron in size. So such a small sample is going to be subjected to a very high pressure, and as a result of which, so obviously it is noticed that there is a change in its morphology. So in order to again to check what might have happened to our samples after getting pressurized to a very high pressure, so after pressurizing, XRD has been taken again, and here are the representative samples of the same material after applying pressure. So XRD pattern of representative samples after pressurization are shown here. So what we can notice here is that the samples still remain amorphous even when they turn near metallic at high pressure. See, what actually used to happen was when chalcogenide glass, basically it's a semiconductor in nature, and when you apply a very high pressure of the order of say 3 to 10 gigapascals, so usually there is a transition which is occurring from semiconductor to near metallic. So that transition is being noticed, and we wanted to know whether the material as such, to check whether our glass, which is amorphous in nature before pressurization, is it being changed to crystalline after pressurization. So to know that, we went for XRD. Again, it is very clear. The samples remain amorphous even they turn near metallic at high pressures. And immediately we did one more thing, that we try to decompress. So in the sense that the way we applied very high pressure from say 0 to 10 GPa, we thought of reversing it. So we did in a reverse order. So when we lowered the pressure from 10 GPa gradually, and we could notice that the same path has been retraced. So there is a retracement of same path. So it is showing that the reversible characteristics. So low resistance near metallic phase is crystalline, with the amorphous to crystalline phase transition being reversible under pressure. The low pressure near metallic phase is also amorphous, with the drop in resistivity arising from a decrease in band gap due to the compression or the moment of Fermi level to the conduction or valence band. So the moment when we apply a very high pressure on our sample, which is very small in size, so as a result, basically being a semiconductor, the moment when you have applied a very large pressure on it, we could notice that there is a decrease in the energy band gap due to the compression or the moment of Fermi level, the conduction band or the valence band. So this is what the another observation that we made before and after pressurization. The exact reversibility, which implies that an amorphous to crystalline phase transition, which with its accompanying structural change, has not occurred. That means there is no structural change as such which is seen. Otherwise, we have just seen the amorphous to crystalline phase transition. Now, again, we plotted a graph by taking resistivity versus percentage content of thallium by keeping at one particular pressure, say a 1.9 GPa pressure has been maintained constant. So I think it's clear from this that there are no signatures of topological thresholds which were observed during this process. And this is very good in agreement with the results of other studies such as switching behavior, ADSC, and all those studies supports the suggestion that added thallium tends to fragment the network. And with this, what I can summarize as a whole is that the electrical resistivity decreases initially with increase of pressure and shows a sudden drop to a low pressure state or low resistance state around 3 to 5 GPa, and then continues being near metallic up to 9.5 GPa. So that's why in the result part of my slides where you could see that there is a decrease in resistivity with pressure. So that is what is being noticed. So transition pressure decreases with increase in percentage content of thallium. So as the percentage of content of thallium is increased, you see that the transition pressure starts decreasing. So this decrease in transition pressure is due to, or it is attributed to, the metallic nature of thallium as compared to tellurium that it replaces. Now coming to the other electrical, experimental evidences like electrical switching studies or ADSC studies, they've really indicated that the thallium is present with two valency, a trivalent and a monovalent thallium. So as thallium content increases, the increasing monovalent species tends to fragment the network, and this may lead to enhanced compression at lower pressures. So, but another point that we observed here, the pressure dependence does not show any change due to valency of thallium present in it. The XRD clearly shows that the sample remain amorphous even after applying or taking back the pressure. So the reversibility suggests two possibilities. Number one, low resistance near metallic phase is crystalline with the amorphous to crystalline phase transition being reversible under pressure. The low resistance near metallic phase is also amorphous with the drop in resistivity arising from a decrease in energy band gap due to compression or the moment of Fermi energy level to the conduction or valence band. The resistivity retraces its path exactly on the removal of pressure, which suggests that an amorphous to crystalline phase transition with its accompanying structural change has not occurred. And also we noticed no signatures of topological thresholds were observed in the present germanium, tellurium, thallium classes. This is in agreement with the results of switching behavior and which supports the suggestion that added thallium tends to fragment the network. Let me come to the conclusion part. So the very first conclusion, bulk germanium, tellurium, thallium glasses exhibit a sudden transitions in their normalized electrical resistivity as a function of pressure undergoing a semiconductor to near metallic transition at pressures around 3 to 5 gigapascals. And second observation, the conclusion, the transition is reversible under the reversal of application of pressure. So which is very important. So this application is going to be reversible in nature. And XRD studies confirms that the samples, all these studies confirm that samples remain amorphous even after undergoing very high pressure cycle. Signatures of topological thresholds were not observed, lending support to the theory that the network is fragmented due to addition of thallium. So I think with this, I will conclude my talk. Thank you very much for listening.